My name's Kevin. I'm from Rice University, and this work was done in collaboration with David Chu and Eduardo Cuervo back at MSR. Okay, so FlashBack's goal is to bring full-quality immersive virtual reality experiences to a weak mobile device. Now, I probably don't have to convince you that VR is on the up and up. There's a lot of cool use cases you can do with VR. But what I want to highlight is that what they all have in common is the need for immersion. You really need that. You really need the user to experience that feeling of presence in the virtual environment. Otherwise, VR just isn't as effective. All right. So the need for immersion places really high demands on computing hardware. So, for example, you need really high graphic complexity, photorealistic scenes with a wide field of view. You need low latency, and you also need a really high frame rate. Mobile devices today cannot meet these demands on their own, like a smartphone cannot render those high-quality frames at a high frame rate. The devices that can do that are things that we call tethered HMDs. So these would be the popular products like the Oculus Rift, Sony PlayStation VR, HTC Vive, products that are tethered to a strong gaming desktop, really beefy GPUs and strong CPUs. So these guys have really good graphical quality and decent responsiveness, but they suffer from mobility issues. And if you don't believe me, here's a quick YouTube video I found to highlight just that problem. Right. So the cord can, kind of get you if you're not expecting it. They're also not affordable, and they require quite a large energy budget. On the other hand, we have this other class of HMDs, which is basically you slot a smartphone into a display, into a head-mounted unit here, and what that will allow you to do is just be completely portable, but the graphical quality there is pretty low. The responsiveness is decent, but that's only because the graphical quality is low. They are more affordable, but the energy budget is pretty poor. For example, the Samsung Galaxy S6, the Gear VR, has an estimated battery life of, I think, about 40 to 45 minutes. So it's definitely underwhelming. Now, compared to these FlashBack's goal is to hit all of these different points and jointly optimize these 5 criteria. The specific objectives of FlashBack are to be self-contained on a mobile device, no offloading, no cloud support, nothing like that. We want to maintain desktop-level image quality, low latency, good energy efficiency so that we have a long battery life, and also equally important is less thermal output because the display is right here. And also no specialized hardware, so it's easily affordable and available. So now I'm going to talk about the design of FlashBack, which realizes these goals. FlashBack is driven by a key insight that we have, which is that on mobile devices today, the GPUs are constrained both by energy budgets and thermal constraints. So there's no active cooling on your smartphone, so you can't just pump up the GPU to run at max all the time. On the other hand, storage on mobile devices is really abundant. It's cheap, it's also low power, and generally underutilized. Right? So from that, we wish to utilize that storage in a better way. And one way we can do that is to pre-render all possible views of a given virtual world such that we can replay them on a weak mobile device at runtime. So that's the key idea behind FlashBack, and we can break its design down into 3 different parts. The first would be the offline pre-rendering stage where we generate those frames, and that's what the rendering memoization aspect comes from in the title. The second part would be live playback, which is done at runtime. And then the third part, which touches on the previous 2 parts, is handling dynamic objects. So first I'm going to talk about pre-rendering, which is an offline stage that suffers from one main challenge, which is infinite input space. So the main goal of the pre-rendering stage is to map a pose to a frame. And a pose is basically the sensor readings that come from the head-mounted display, the Oculus device, for example, and it consists of 2 values, one 3D position and one 3D view orientation, which is basically the rotation of the user's head, where they're looking. And we want to map that to a frame. Now the problem with this is it results in an infinite input space, right? There's an unlimited number of positions you could be at, view rotations, etc. So instead of doing that, for a frame like this, what we do is we capture a cube map. And a cube map, clicker's not working. A cube map is a classic computer graphics representation of a scene that captures all the possible view orientations. All right, we do this by capturing front, back, left, right, up, and down cube faces of the surrounding environment. Now, we also do this with a special camera that captures the depth values of each pixel. And this is important for reconstructing the 3D scene later at runtime from the 2D scene. And we also use it for some other things, which I'll show later. So what cube maps allow us to do is to remove and have the input space. We can remove the 3D orientation value, so we only have 3 dimensions to explore in the input space, which is the X, Y, and Z of the position. Now, when we have this, when we have these cube maps, we arrange them into a megaframe. And a megaframe is basically the color and depth cube maps for each eye, left and right. We need left and right eyes to properly reconstruct the depth scene that you'll see with both of your eyes. And then what we do is these are the values that are stored in the cache. So instead of mapping a 6D pose to a frame, we map a 3D position to a megaframe, because once again, the megaframe contains all the possible view orientations for a given position. Okay? So there are other ways we can reduce the input space. The paper gives more details on these, but I'll briefly highlight some of them. One of them is since we automate the iteration over these possible inputs with whatever game engine we're using, for example, Unity, we can prune unreachable positions. For example, it doesn't make sense to capture a megaframe when I'm standing underground or inside of a wall. Right? The second thing is we have configurable quantization granularity. And quantization is just the technique, just the term I use to describe how we discretize the continuous virtual world into little chunks. Right? So a finer quantization means I'm capturing more dense chunks. I'm capturing the environment with more density, and coarser would be sparser. All right. So in summary, after the pre-rendering stage, what we have is a full coverage frame cache that covers the entire virtual world available to the mobile device at runtime. Okay, the next stage is live playback, which happens on the mobile device. The two main challenges here are that we have a huge cache of megaframes, but we want to maintain fast retrieval so we can have low latency and a high frame rate. The other challenge is because I'm quantizing the virtual environment, you're not going to have a megaframe available at every single position. So we need to have inexact query matching. So just to step back for a moment, here's an overview of how the live playback works. We capture the pose, which is a sensor reading from the Oculus Rift, and we use that position value from the pose to index the megaframe cache, which is this inverse pyramid thing here. And then when we grab the proper megaframes, one or more megaframes, we use a cube warp technique, which is also from the graphical community, to reconstruct that scene based on the megaframe. The cube warp also allows us to do a quick and cheap approximation. For example, if we can't deliver a frame in time and we still want to maintain a high frame rate, we can use a previous one and warp it a little bit to appear from a new perspective. And this is a common technique. And then when we have that final frame come out of the cube warp, it's then sent to the Oculus, which does some warping to offset for the lenses and then displays it on the screen. So let's take a look at how we build this cache. So when the runtime starts, everything is stored on secondary storage, which I'm going to use CPU cache terminology because they're similar, is L3. All right. Now L3 is the largest storage. Typically on a smartphone it can be 64, 128, and in the future 200 plus gigabytes. And we need that storage because some of the frame caches can be 40, 50 gigs. This offers a retrieval time, which means the time it takes, once I've searched the cache, the time it takes to grab a megaframe, bring it down into the GPU so we can display it, of about 9 milliseconds. Now, if that frame is stored in system RAM, that time goes down a little bit because we don't have to ask Flash for it, but it's still about 8.7 milliseconds. Now, we actually need to serve the frames from the GPU, which offers a very fast retrieval time because they're already decoded and ready to go on the GPU. So all we have to do is blit it to the screen. I should mention that only the GPU stores the megaframes in a decoded fashion. Both the upper two tiers of the cache, they store the frames in an encoded format, which is basically just compressed with some video codec like H.264. So what this allows us to do is maintain a really huge cache, like millions of frames, but also offer fast retrieval so we can have a high frame rate and low latency. So once we have this cache, we need to properly index it. So the picture on the left here shows an example of a logical representation of the megaframes or the cube maps in 3D space. Each silver cube is a megaframe at a given position. The camera icon, the white little camera icon there, shows where the player currently is. And the problem is that I need to find the closest matching megaframe, which is obviously this one in the center, but it's difficult to do that quickly. So to make a long story short, for this we use R-trees, which is a spatial search algorithm that constructs a set of minimally overlapping bounding boxes, such that you can eliminate large portions of the search space very rapidly. All right, so this allows us to find the nearest neighbor pretty quickly. We maintain two different indices into the cache. It's the same cache, but indexed twice. One is a universal index that allows us to find the best megaframe, no matter in which tier it's stored. And then the other one is a GPU-only cache, which allows us to reduce latency if we have a better matching frame that's ready to go immediately, right before we've already displayed everything else. So this is how we implement inexact query matching. Now I'm going to talk about dynamic objects, which touches both of the previous stages. So dynamic objects are an extension of the static scene. They have, instead of a 3D input space of just the position, they have a 7-dimensional input space, which is their position relative to the player, their rotation, which is the rotation of the object itself, not the player, and an index into the animation sequence, which is basically just what part of the animation are you in. So here's an example of how we capture the megaframes for a given dynamic object, like this cute little horse cart here. What this does is what this shows is that each little camera icon is where we would capture a megaframe from. So we want to capture a representative sample of every angle of this dynamic object, basically. What this allows us to do is support arbitrary motion paths and animations for any object. Now, it seems like animations would be really, unbounded, but they're not. Typically, they're very periodic, and they have relatively short periods. So we actually don't have to capture too many. So for example, in this demo that I'll show in a little bit, we only had to capture about 30 animation frames for this particular object. And then at runtime, we have to extend the cache indexing policy to support dynamic objects as well. A 7-dimensional query is just not that meaningful, right? So what we do is we decompose this into a chain of queries. And there's more information on this in the paper, but basically what happens is we first query for the position, and then we query for the orientation based on that position, and then we query for the animation given that previous orientation and position, right? So this actually has the upside of allowing for really fast queries. We can prune the search space pretty aggressively at each level of the query. And then finally, once we have the megaframe shown here in the middle for that particular object, or this is just one cube face, but once we have that megaframe, we need to combine it with the static megaframe such that everything looks nice and proper. And this is where those depth values come back into play. So for example, here this horse cart is appearing in front of everything, but if we wanted to, we could nestle it between one building and another. So it could appear properly within the scene for a particular z-value depth. Okay, so that's basically the design of FlashBack. Now I'm going to talk about how we evaluated it. We implemented FlashBack on an HP Pavilion Mini, which is a really, really weak entertainment computer with no graphics card, no discrete graphics card. And the VR headset we used was the Oculus Rift DK2. So this is an approximation of a mobile device because our implementation was Windows-based, and also because the VR HMDs right now that run Android are not fully open. This actually underperforms the state-of-the-art Gear VR system by almost a factor of 2x in these graphics benchmarks. And both of those devices are about an order of magnitude weaker than a standard desktop computer that would support the Rift directly. So without further ado, here's a video demo. This is FlashBack, a scene from a game called Viking Village. And you can see that everything's nice and smooth. The frame rate is high. The latency is low that you can't tell here. And we do support dynamic objects like this little horse cart moving around. All right? So compare that same scene to local rendering, and you can see that it's less than satisfactory. And that's the understatement of the century. Local rendering here achieves about 8 to 9 FPS and nearly 300 milliseconds of latency. So it's pretty unwatchable. Now, to put specific numbers behind these demos, we achieve about a 15 times higher frame rate than when the mobile device is rendering it locally. We also achieve about 8 times lower latency, and there are some nuances here, but you can find those details in the paper. We also, which is I think even more important, is we reduce the energy consumption really significantly. Now, this 97 times figure is rather high, but that's because it's a per frame figure. So this doesn't necessarily result in 97 times longer battery life. We're just delivering more frames. But it will certainly improve the battery life, and more importantly, there will be less thermal output, so it'll be very comfortable. All right. Finally, the last part of the evaluation is that FlashBack maintains the same visual image quality that a strong gaming desktop would produce. So in this case, we use the structural similarity metric, which is a standard objective metric for visual, the quality of an image. And what we do is we compared the rendered scene from FlashBack with a pristine image as rendered on the desktop machine. So comparing it to what happens on a local device, with local rendering on the mobile device, the SSIM indicates that this is very poor quality, but FlashBack achieves much higher quality. So we don't introduce any visual artifacts or problems like that. Now, I do want to be transparent that there are some limitations of this approach. Right? First, the scalability of dynamic objects is only moderate. We can only scale to maybe 6 or 7 particular objects on this very weak device. Right? So this is because of the way that we're compositing the images in the pixel shader. We're comparing each pixel. And there are some optimizations there. But still, the scalability is not amazing. But one upside to this is that the object complexity is irrelevant. So it can be any sort of really complex object, but it doesn't matter because we pre-rendered it already, so it doesn't even matter what sort of animations or anything it has. It can still be done. Also, I should add that if you have 20 instances of like some sprite that are moving all at the same time, that can just be considered one independent object in FlashBack. Another thing is that we have lighting models, some complex lighting models such as reflection or specular diffusion, and these things are not easily supported because the lighting of one object affects another one, and we can't necessarily support that with rendering, though that is part of the future work. Sorry, we can't support that with pre-rendering, I should say. And then finally, we have some restrictions by the hardware decoder, but it's nothing too bad as we expect these to improve over time. I want to briefly touch on some related work that we built off and compare it with FlashBack. So pre-caching has been around for a while, but in general, the VR domain has a lot of different design decisions made. Offloading is also very related, but we want to use that local storage, which offloading does not, and we want to reduce latency. Okay. Finally, caching images as rendered objects has been done before, but not to the extent that we can support a game like what you saw in the demo. Apple has a product called QuickTime VR, which basically allowed you to have free viewing through a static video, but it doesn't support dynamic objects. And then finally, the concept of warping cube maps, to approximate a new frame or to reconstruct a 3D frame is also not new. But previous efforts to do this in VR have required specialized hardware. All right, so in conclusion, FlashBack is a technique to bring really good, immersive, full-quality VR experiences to weak mobile devices that generally would not be able to support them otherwise. It has kind of an interesting side effect in that it flattens the complex behavior of a VR application into a set of simple data structures. And all you have to do to load a new game is just swap those data structures. We support both the static scene and dynamically animated objects, and we realize a significant improvement in frame rate, latency, and energy. That concludes my presentation, and thanks so much for listening.